Imagine a world where numbers are studied in isolation. Maybe, first year of school, you study the number 5, and you do various things with the number 5. Maybe there is a class at university about the number 24, and some research group in Paris are experts on the number 57. They only think about 57 all day and night. In this world, no one has ever imagined that some numbers belong together in families, like 1, 2, 3, 5, 8, 13, 21, 34, based on a common recursion, or like 2, 3, 5, 7, 11, 13, 17, 19, a family based on a common property. Maybe it has been noticed that numbers could be added, like 4 plus 5 is 9, but that is seen as unnatural. Numbers 4 and 5 shouldn't be combined or in general allowed to go near each other. Our ordinary concept of multiplication is unthinkable in this world. And relationships like 4 is a divisor of 24 or 5 is the square root of 25. No. That is not how we talk about numbers. Previously, in the RH Saga, we have talked about L functions, mostly as if they were isolated objects. If that is all we do, we place ourselves in a world like the one I just described. We make ourselves blind to unfathomably rich structures, emerging only in the relationships between different L functions. L functions can be combined to make new L functions. And L functions often do belong together in families. Today, we shall begin the journey towards a better world by talking about operations on L functions. Some of these operations are well understood and rigorously defined, while some are still the subject of very active and difficult research. A family of L functions can be thought of as a sequence of L functions that have something in common. Maybe there is a fixed rule for how to pass from one L function to the next, or maybe the sequence contains all L functions that satisfy some specific properties. Formally, you can think of a family as an operation that, for every natural number n as input, gives some L function as output. Here is one example. I can write down the family of equations y squared equals x cubed minus n squared times x. So for n equals 1, it's y squared equals x cubed minus 1x. For n equals 2, it's y squared equals x cubed minus 4x. And for n equals 3, it's y squared equals x cubed minus 9x, and so on. Each of these equations has an L function. We could say L1 of S, L2 of S, L3 of S, and so on. This sequence is a family of L functions, coming from a family of equations, in this case, a family of elliptic curves. This specific family is quite famous because it's related to a problem called the congruent number problem, which asks what are the integers n such that some right-angled triangle with rational sides has area n. An example. There is a triangle with legs 3/2 and 20/3 Pythagoras gives 41 over 6, surprisingly, a rational number. The area of this triangle is 3 over 2 times 20 over 3 divided by 2. That's 60 over 12, so that's 5. So this triangle shows that 5 is a congruent number. It's a classical problem, which in general is very hard to determine whether a number n is congruent or not. And this problem turns out to be related to a value of the corresponding L function in the list we had. And it's the value of the L function at the point where the critical line meets the real axis. That's the central point. I will list some references for congruent numbers in the course notes, and these are a really good way to begin learning about elliptic curves. The simplest of all families may be the family coming from primitive real Dirichlet characters. This one we can find in the LMFDB as follows. From the front page, we click Dirichlet characters. Then in the search, we say primitive yes and real yes, and then list of characters gives us the family. Here, 1.a actually gives the Riemann zeta function, and 4.b gives our periodic example, the one we called A before. So, if we click at the Connery label here, and that's Brian Connery from episode 1, and then go to the associated L function, you see all kinds of data. The Dirichlet series, the functional equation. The degree of this L function is 1, the conductor is 4, and the same degree is also visible from the Euler factors. Here you see that the local polynomials are all of degree 1, except at the bad prime p equals 2. Anyway, the point here was that our examples P and A from earlier episodes belong to an entire family of L functions. And there are patterns to explore in this family and questions that couldn't even be asked as long as we think of the L functions as isolated entities. Our first binary operation on L functions will be addition, also referred to as direct sum. We use this symbol for addition, a plus, encircled by a circle. The definition of direct sum is that for two L functions, say L1 of S and L2 of S, the direct sum L1 plus L2 of S is L1 of S times L2 of S. Now, this may look confusing at first. We define addition of L functions to be multiplication of the Dirichlet series. We could not have used addition on the right-hand side, since if we just added the two Dirichlet series, the result would not be an L function. The main problem being that this Dirichlet series does not have an Euler product. So adding Dirichlet series is simply not a valid operation on L functions. But why multiplication? This could be explained and motivated in more detail by talking about the primal objects that the L functions often come from. For example, if you have two equations, they have graphs, and taking the disjoint union of the two graphs will correspond precisely to multiplying the Dirichlet series. In topology and other contexts, disjoint union is thought of as addition. For example, the disjoint union of 4 stones and 5 stones would be 9 stones. Or, if you know some category theory, taking the direct sum of 2 motives, or the isobaric sum of 2 automorphic representations, will again correspond to multiplication, not addition, of the Dirichlet series. Let's do an example. Say I have the L function of P and the L function of A. I will compute their direct sum. The first coefficient is 1 times 1. That's 1. The second coefficient is 1 times 0 plus 1 times 1. That's 1. The third coefficient is 1 times minus 1 plus 1 times 1. That's 0. The idea is that for the fourth coefficient, I have to think 1 times 4, 2 times 2, and 4 times 1. That's all the factorizations of 4. So I take 1 times 0 plus 1 times 0 plus 1 times 1, and that is 1. The fifth coefficient is 1 times 1 plus 1 times 1. That's 2. Let's do one more. The sixth coefficient is 1 times 0 plus 1 times minus 1 plus 1 times 0 plus 1 times 1, and that is 0. The first 8 coefficients of the direct sum are 1, 1, 0, 1, 2, 0, 0, 1, and maybe you now recognize this sequence. This is the L function of the equation k, which was x squared plus 1. This method for sequences is called Dirichlet convolution. It gives you the product of the corresponding Dirichlet series, but look at what happens for the primes. 1 plus 0 is 1. 1 plus minus 1 is 0. 1 plus 1 is 2. And 1 plus minus 1 is 0. At each prime index, this is just ordinary, traditional addition. Anyway, the upshot here is that the L function of P plus the L function of A is the L function of K. And this is a more precise explanation of what we did back in episode 2 with a triangular table where we constructed the sequence of K based on finding the pattern of A along the diagonal. Let's do one more practice example of Dirichlet convolution. 2 very simple sequences are 1, 1, 1, 1, 1, 1, 1 and 1, 2, 3, 4, 5, 6, 7. In this case, the Dirichlet convolution is 1 times 1, that's 1. 1 times 2 plus 1 times 1, that's 3. 1 times 3 plus 1 times 1, that's 4. 1 times 4 plus 1 times 2 plus 1 times 1, that's 7. Then it's 1 times 5 plus 1 times 1, that's 6. And then we get 12, 8, and so on. And this is the sigma function from the previous episode. We have done addition. Now, multiplication. This is also called tensor product, or sometimes Rankin-Selberg convolution. And this is a much more mysterious and complicated operation on L functions. In fact, if you take two L functions, so L1 and L2, satisfying all the axioms from the last episode, in many cases it is not known that the tensor product also satisfies the axioms. We believe for sure that the tensor product of two L functions is always well-defined and that it is an L function. But to prove this, in general, is a part of the Langlands program, related to the theme called functoriality. The principle is that to compute the tensor product of two L functions, you need two steps. First, a main step, and then a correction step. I will do this now for a few examples. Recall that we previously used these four L functions. The L function of P, the L function of K, the L function of A, and the L function of E. The L function of a point, that is the Riemann zeta function, is the identity element for the tensor product. So LP times anything, say LE, is just that same thing. In this case, LE. Let's compute LA times LA. So LA is this periodic 1, 0, minus 1, 0, 1, 0, minus 1, 0. The main step in this case is quite easy. I simply take 1 times 1, that's 1, 0 times 0, that's 0, minus 1 times minus 1, that's 1, and so on. That was the main step. The correction step in this case is that all the even indexed numbers have to be changed from zeros to ones. The result is the Riemann zeta function. So LA times LA is LP. Now let's do LA times LK. Here, the first one, LA, has degree 1, and the second one, LK, has degree 2. And whenever at least one of the factors has degree 1, the main step is easy. It's just like before. 1 times 1 is 1, 0 times 1 is 0, then it's 0, 0, 2, 0, 0, 0, 1, 0. The correction step in this case begins with changing the numbers at 2, 4, 8, 16 at the powers of 2, and they have to be changed from zeros to ones. At the powers of 3, so that's 3, 9, 27, we just keep the numbers from the main step. At the powers of 5, that's 5, 25, and so on, we also just keep the numbers. It's the same for all odd primes. Finally, at position 6, I have to multiply the numbers from position 2 and 3, and that gives me 0. And at position 10, I have to multiply the numbers from positions 2 and 5, so that gives me 2. Now, if you compare the second row and the last row, you see that they are identical. And the upshot of this computation is that LA times LK is actually LK. Another way to think about this specific computation is to use that tensor is distributive over direct sum. So we do LA times LK again. Now using the previous result that LK could be decomposed as LP plus LA. Now we compute. LA times LK equals LA times, and I substitute the sum, LP plus LA. By distributivity, I get LA times LP plus LA times LA. The first one is just LA, since LP is the identity element, and the second one is just LP. That's the computation we did earlier. All in all, LA plus LP is LK, and that's the answer. We could also try LA times LE. The main step would be easy, just like before, since LA is of degree 1. But now the correction step is too complicated for me. I don't know how to do it in this example. So what is the underlying principle for the tensor product in general? How would you compute it in principle for more complicated examples? For the main step, the idea is to work not with the entire sequence like we just did, but instead with the individual Euler factors. For one prime at a time, we would take the tensor product of the local polynomials. Well, what does that mean? The idea is that if you have, for example, the polynomial 1 minus 3t times 1 minus 5t, and the polynomial 1 minus 2t times 1 minus 7t, then the tensor product would be 1 minus 6t times 1 minus 21t times 1 minus 10t times 1 minus 35t. So for each prime, you can compute that Euler factor from the two original Euler factors from the same prime. And once you have all the Euler factors, you expand the infinite product, the Euler product, to get the actual Dirichlet series. That was only the main step. For the correction step, the idea is to go back and possibly adjust or change some of the Euler factors for the bad primes. For a bad prime, you can find the right Euler factor either theoretically, based on so-called ramification theory, or numerically, by trying all possible Euler factors until you get this functional equation, the perfect symmetry in the graph that we talked about last time. So far, we have talked about two binary operations, where we take two input L functions and combine them into a single output L function. There are also many unary operations taking one single L function as input and transforming it into a new single L function as output. Many of these unary operations have a certain internal symmetry, and those operations are called lambda-operations. The first example of a lambda operation is the so-called central character operation. This machine takes an L function as input and produces another L function, always of degree 1, as output. Two examples. The central character of LK is LA, and the central character of LE is LP. Another lambda operation is the symmetric square operation. Here, input of degree 1 gives output of degree 1, input of degree 2 gives output of degree 3, and input of degree 3 gives output of degree 6. The right-hand side here are the triangle numbers, 1, 3, 6, 10, 15, and so on. One example, the symmetric square of LK, which has degree 2, would be LK plus LP, which has degree 3. That's not very interesting because P and K, those are L functions we have seen before. Let's go to the LMFDB and find our elliptic curve again, labeled 14.A5. Here you can click on the L function and then its symmetric square, and this L function is very interesting. It is our first L function of degree 3 that cannot be decomposed as a sum of simpler components. We didn't define the last two operations. The principle behind the definitions is similar to the one for tensor product. There is a main step where the computation is done for each Euler factor or each local polynomial. And then there's a correction step which is complicated. Let's do the main step. For the central character operation, 1 minus 3t would give 1 minus 3t. But 1 minus 3t times 1 minus 5t would give 1 minus 15t. And 1 minus 3t times 1 minus 5t times 1 minus 7t would get 1 minus 105t. That's 3 times 5 times 7. For the symmetric square, 1 minus 3t goes to 1 minus 9t. So that's the square of 3. 1 minus 3t times 1 minus 5t is sent to 1 minus 9t times 1 minus 15t times 1 minus 25t. So the square, the product, and the other square. Finally, if you have 1 minus 3t times 1 minus 5t times 1 minus 7t, that would go to the degree 6 polynomial with t coefficients 9, 25, 49, 15, 21, and 35. All the squares and all the pairwise products. In all cases, for the central character and the symmetric square, the operation is symmetric in the coefficients of t, the numbers we used to square and to multiply. And this symmetry is the internal symmetry that I mentioned earlier. So, just to recap again, lambda operations are computed separately for each Euler factor, like the tensor product, and then there is a correction step for bad primes that we didn't talk about today. Just like for the tensor product, lambda operations are not known to be well-defined operations for all L functions in general. This well-definedness would again be a consequence of results within Langland's functoriality. Some L functions can be decomposed as a sum. For example, the one from K comes from A and P. When an L function cannot be decomposed in this way, we say that it's primitive. We could also have said irreducible. We can picture all the primitive L functions as unit vectors in a coordinate system. Non-primitive L functions then appear as other vectors in the same system. For example, K would be P plus A, like this. The L function of E is primitive and would be a third unit vector, not in the same two-dimensional plane, but in the third dimension, so like x, y, and z axis. If you take all primitive L functions, and there are infinitely many, Taken together, they form a basis for an infinite dimensional vector space. For example, LA, inner product LP, these are orthogonal, so the inner product should be 0. LK, inner product LK, should be sort of the square root of 2 times the square root of 2 times cosine of the angle 0. So that would be 2. How do we define this inner product? Conjecturally, you can use this procedure. Let's say we have L1 with coefficients A1, A2, A3, A4, A5, and so on. And some other L function, L2, with coefficients, say, B1, B2, B3, B4, B5. Now I use only the primes, and I take A2 times B2 divided by 2, plus A3 times B3 divided by 3, plus A5 times B5 divided by 5. And I do this up to some bound x, say prime numbers up to 5 in this case. I then divide by log of that bound, in this case log of 5. And all of that is just some very concrete number. I can do this again for some larger bound x. I take the sum of AP times BP divided by P for all primes up to that bound x. Then I divide by log x. Again, that's just a number. Finally, I take the limit of these numbers as x goes to infinity. If the limit exists, it's some number again, and this number is, by definition, the inner product of L1 and L2. One example would be LK, inner product LA, that equals 1. And the two previous examples also behave as we expected. For some pairs of L functions, it is known that this limit exists and that it is an integer. In general, that is a conjecture. Okay, we have talked about families of L functions, addition and multiplication of L functions, about lambda operations, and the Selberg inner product. These 5, I would say, are the most important, but there are also other operations we'll encounter later. Just a few remarks. First, when some set has a well-behaved addition and multiplication, then we call it a ring. If there are also lambda operations, we have a lambda ring. Think about the set of all L functions. And let's start thinking about this as a lambda ring, even though many of the operations are still only conjecturally well defined. I like to use the notation L for the set of all L functions. I want to call it the absolute Grothendieck ring. And I think it should be viewed as a fundamental object of mathematics, very much like, say, Z or R. Second, having an inner product on a vector space of countable dimension means you have something that looks like a Hilbert space. Indeed, we shall think of L both as a lambda ring and as a Hilbert space. And these two perspectives open up all kinds of analogies with other similar objects in physics and mathematics. There are lambda rings in representation theory and in the theory of symmetric polynomials, and we can import ideas from those fields into our study of L functions. If you like physics, maybe you are used to thinking of vectors in Hilbert space as physical states. By analogy then, L functions are like the state of some physical system. Maybe the Riemann zeta function is like the vacuum state. I have a book recommendation. Many popular math books suffer a little bit from oversimplification. This book is different. It's by Avner Ash and Robert Gross. I absolutely love that they have opening quotes by William Blake about teaching and about fearful symmetry. The book is called Fearless Symmetry. In the table of contents, you will find many of the things we talk about in Season 1 of the RH Saga. They make a very serious attempt to explain everything from scratch. There is some group theory, some complex numbers, equations, quadratic reciprocity, doing things mod p, like we did. Then they talk about elliptic curves and Galois representations. So that's the third part of the Langlands universe of primal objects. The entire part 3 is about reciprocity laws more general than quadratic reciprocity. They construct some Galois representations and they connect everything to Fermat's last theorem. At the very end, they also talk about the congruent number problem we mentioned today. Next time, we will talk about invariants of L functions.